Hello, everybody. This is Nafrit Sekho, and I welcome you on this platform, The Layers of Life Sciences, where we are discussing various aspects of life sciences in quite depth and detail, layer by layer. The objective is not just to help you in your graduation, post graduation, and competitive exams, including CSIR NET, but also to have a discussion about the life processes happening around us. We have started with biochemistry, and in that, we started the discussion with the structure of carbohydrates. In last four videos, we have discussed the linear as well as the cyclic structures of monosaccharides, which are the basic building blocks of carbohydrates. On the way onset of that discussion, I underlined the point that whatever structures, linear or cyclic, we are learning to draw, they are just the 2D representations of the 3D molecules. So today, let's learn how these 2D representations, which are also called formulas or the models of the 3D molecules, how these 2D formulas and the models are related to the actual 3D structures of these molecules. This is a very interesting aspect. Let's learn it. In the video Biochemistry 2, when we were discussing stereoisomerism in case of aldoses and ketoses, there we discussed that if we need to perceive the structure of an asymmetrical subject, which can be a normal object or it can be any molecule as well. So if we want to perceive the structure of any asymmetrical subject, then in that case, the position of the observer and the position of that subject will matter. If any one of those, like position of the observer or the position of the subject is changed or it's altered, then the perceived structure will also change accordingly. Same thing happened with the scientists who were trying to formulate the methods, the formulas, the models to represent the complex 3D molecules on the 2D surfaces. The first scientist who tried to formulate a method gave us this wedge dash formula. Now, in this wedge dash formula, generally carbon compounds are used to represent as wedge dash formula because in biochemistry also and in chemistry also, we are using all these formulas for representing the hydrocarbons, means the molecules which are largely formed of carbons and hydrogens. As we have done in the video Biochemistry 1, that carbon is tetravalent. Now, if carbon is tetravalent, then it may fulfill its 4 valencies by covalently binding to 4 different groups. In that case, that carbon will become chiral, or 4 same groups, or any 2 of them can be same, 2 may be different. So it can be anything, right? So all these cases of carbon being fulfilling its valencies in any of the ways can be represented by this wedge dash formula, right? But because if a carbon is chiral, the case can be more complicated. So we have taken the example of a chiral carbon over here, which is bonded to 4 different groups. This is A, B, D, and E, right? So these four are the 4 different groups which can over here be represented by these balls. So this black ball over here represents the chiral carbon. This green ball represents A. This blue ball over here represents B. And this yellow ball represents D. And here this white ball represents E. Now, what Kekule said that whenever I want to draw the wedge dash formula for any molecule, I will keep the molecule in such a way that this chiral carbon and 2 of the groups bonded with it, for example, over here A and D, right? 2 of the groups A and D, they should be in the same plane. So this triplet should be in the same plane, right? So these, it can be any three, although it can be this one as well. This can also be the triplet, right? It can be any two of the bonded groups should be in the same plane as the carbon is, like this, right? But here we are taking the example that A, B and this carbon are in the same plane, right? So he says that when two of the bonded groups are in the same plane as the carbon is in, so in that case, one of the group will come out of the plane towards the observer. Over here, I am taking you as the primary observer, right? So now if you see, this is the group which is coming out towards you. So these three are in the same plane. This is coming out of the plane and it is coming out of the plane towards you. And other group, the fourth group, will again go out of the plane, but it will point away from the observer. He said that the groups which are in the same plane as the carbon is, those will be represented by these simple bond lines, right? Simple lines. The group which is coming out of the plane towards the observer should be represented by this wedge line. So over here, see, D is being represented by this wedge line. And the group which goes out of the plane away from the observer, this one is just away from you, right? Away from the observer, then that should be represented on the 2D surface with this dash line. So this was what Kekulé suggested, that this is how you can show 3D molecule on a 2D surface. Over here, if you will visualize that all the angles, the angle between all these groups is 109 degrees. Okay, it is an obtuse angle, right? It is, they are not at 90 degree to each other, they are not even at, and they are not existing in straight line to each other. So all the angles between all the molecules over here is actually an obtuse angle, and this angle, this shape is called the tetrahedral shape. This will always exist if some atom will try to fulfill 4 of its valencies with 4 single bonds. Then in that case, always a tetrahedral structure will be formed, and this angle between the two groups is called bond angle. This angle is called bond angle, and that bond angle, the value of that bond angle will always be 109.5 something, right? So this bond, in this structure, all the bond angles have been taken into consideration. If you will see, this structure is also called wedge dash structure, and this structure was given by Auguste Kekulé. Now, then the next was about Fischer. Now, Fischer said, okay, he wanted to observe the same molecule. Now, but he said that I don't want to observe the molecule from this side. How he said, he rotated this molecule like this, right? First he rotated. So it was the actual position. He rotated the molecule like this, and then tilted it like this, right? He said that none of the bonded groups would be in the same plane as the carbon. Earlier, 2 of them were in the same plane when Kekulé did it. But now, Fischer is saying none of the bonded groups will be in the same plane as the carbon. So carbon is the only thing which is in the plane. So let's do it. This is the carbon, the black carbon. Okay. So if this is the carbon, then 2 of the groups will be going out of the plane away from the observer. So this right now, this green ball and white ball over here are again out of the plane. None of them are in the same plane as the carbon. Carbon is the only thing which is in the plane. So these 2 are going out of the plane away from the observer, and they will be represented on the vertical line around the carbon. On the 2D surface, they will be represented on the vertical lines. So over here, I can represent this green ball. and then over here I can represent this white ball. Just a white ball. Then the two groups which are again coming out of the plane, but towards the observer, the two groups which go out of the plane but towards the observer, they need to be represented on the horizontal lines. So they will be represented on the horizontal lines with blue over here and the yellow group here. So now you can see that this is the position from where Fisher was observing a molecule, right? Where only carbon is in the plane, all its bonded groups are out of the plane. The two groups which come out of the plane towards the observer are represented on these horizontal lines, while the two groups which are going out of the plane but away from the observer, then these are represented on the vertical line. Now, point to be again mentioned, I am taking you as the primary observer. Don't take me as the observer, right? I'm taking you as observers, primary observers. So they are pointing towards you, the observers. So that's why they are represented on the horizontal line. So this was the basic idea behind the Fisher projection. In Fisher projection, he didn't take into account the bond angle. Over here, bond angle is being considered of the tetrahedral shape, right? But here he said no, just represent the things on horizontal and vertical lines. It is just a representation after all, right? Why we need to include bond angle over here? So this was Fisher projection formula, and now this formula we have used extensively while doing the linear structures of the monosaccharides. Let's try to visualize that structure. This is actually the linear structure of aldohexose, right? So this is aldehyde over here. This is aldohexose 2,4,5. So this is the glucose structure over here. So now let's try to visualize it in the 3D perspective. So this is the actually linear structure of the same molecule, which is represented over here in the 2D form. So first of all, let me tell you the representations. All the black balls over here are representing these carbons. Carbon number 1 to carbon number 6. So it is carbon number 1, then this is carbon number 2, carbon number 3, carbon number 4, carbon number 5, and carbon number 6 over here, right? So this is the these all black colored balls are the carbons. This orange colored ball over here is representing our oxygen. All the white balls over here are representing the hydrogens, and all the red balls are representing the OH groups. Now, I have not taken two differently colored balls for O and H separately, just for the simplification. I should have taken, that is the exact way to do it. But if I would have done it, then this structure would have become further complicated. And we need to understand the relative positioning of the atoms in this molecule, right? So why to complicate the things? So I've just tried to simplify the things by representing this OH just with this red ball over here. Let's see how these atoms are organized in this glucose molecule. So this is carbon number 1 over here, right? And on this carbon number 1, this oxygen is bonded by a double bond. I have shown the double bond with the shorter as a shorter bond because double bonds are shorter than the single bonds. And on the other hand, this H is being represented by this white ball. So this carbon is the carbonyl carbon. So this is the achiral carbon, and on this achiral carbon, these structures are actually not drawn vertically to this carbon because the positioning of these two groups doesn't matter. Carbon is shown on the vertical line. So it means this is carbon number 1 and this is carbon number 2 over here, right? So it should be pointing away from you. right? So it should be pointing away from you. It means if this is the bond, carbon, this is the carbon which is in the plane. Now this needs to be pointing away from you, this carbon number 2. Now, after this carbon number 1, we come to the first chiral carbon, which is the carbon number 2 over here. Let's see. And now it has all the vertical bonds, vertical lines, and the horizontal lines around it. So on the vertical lines, it is C1 and C3. Right, so any group which is on the vertical line, it means it should be pointing away from you. So this is carbon number 1 and this is carbon number 3. They both should be pointing away from you. So it should come like this, right? It should come like this. So this carbon number 1 and carbon number 3 over here are just going out of the plane away from you, the observers. Right, now about these two, they are again going out of the plane, but they are going out of the plane towards you, right, towards the observer. So that's why they are being represented on the horizontal lines. Right, now after carbon number 2, we come to carbon number 3. Again, on carbon number 3 over here is bonded with carbon number 2 and carbon number 4. Carbon number 2 and carbon number 4 over here. So now the point of reference is our carbon number 3. So if this is carbon number 3, this carbon should be in the plane. So this carbon number 2 is pointed away from the observer, just like this carbon number 4 over here. Carbon number 2 and carbon number 4 over here. While these two groups on the carbon number 3, which is one is H and another one is OH, they are again going out of the plane, but they are pointing towards the observer, pointing towards you. Same thing happened with the carbon number 4. Carbon number 4 is bonded with carbon number 3 and carbon number 5. So this is the carbon number 4. This is the carbon number 4. Carbon number 4 over here is bonded with carbon number 3, and another side it is bonded with carbon number 5. So this carbon number 3 and carbon number 5 both should be pointing away from the observer. So if they will point away from the observer, then this will be the situation. Right, so they are pointing away from, this is carbon number 4, this carbon number 3 and carbon number 5, both are pointing away from the observer and they are going out of the plane. These two groups, OH and H, both are again going out of the plane, but they are just pointing towards the observer, going out of the plane towards the observer. So that's why they are represented on the horizontal line. So same thing will happen with this carbon number 5. Carbon number 5 is attached to this. Carbon number 5 is attached to this carbon number 4. This is carbon number 5. Carbon number 5 is attached to this carbon number 4 and this carbon number 6 over here. So here also both, because carbons are on the vertical line, so all the carbons should be pointing away from you. This carbon is in the plane because right now this is the carbon of reference. This is in the plane. These are going out of the plane away from the observer, and these are again going out of the plane but towards the observer for carbon number 5. This was the last chiral carbon. Now carbon number 6 is on the vertical end. It is bonded with this carbon number 5. It must have been bonded with one more group on the vertical side, but here it can be any of the two H's, or it can be OH, it can be anything. Let's see what is over here. This is carbon number 6. Carbon number 5 should certainly be pointing away. With this right now, OH is pointing away from the observer, that is you, and two H's are just facing you, right, are pointing towards you, going out of the plane. So this is basically the linear structure of glucose, which is not, I know, which is not that linear. It is quite turned and twisted. This is linear. This 2D structure is linear because we are actually ignoring the bond angles between the groups bonded with the central carbons, and that is good because we need to draw the structures in the simpler manner, and that was the point of Fisher. So this was the Fisher projection formula. And this is how we can relate the Fisher projection formula with a 3D structure. This we can do with any Fisher projection formula. Now, another formula which we actually used extensively was this Haworth projection formula. Now, Haworth projection formula we actually used for the for drawing the cyclic structures of all the aldoses and ketoses. Now, over here, if you will visualize that we were doing we knew that the cyclic structures can be hexagonal or pentagonal, which we refer as the pyranose or the furanose rings, right? And we drew them as well in the video number 4. But we never drew the base of those hexagonal and the pentagonal rings in this in this manner, right? Like these three bonds are actually not represented by the simple bond lines. They are being represented by again the wedges, right? Or we can say the black strip. Why so? The reason is that actually Haworth is saying that when we need to observe the structure of any cyclic structure, we should be observing from this direction. So as we discussed, that direction from which we are observing, the angle from which we as the observer are observing, and our subject is lying, that matters, right? So over here they are making it clear that from where the Haworth was observing while drawing these structures. So he said when we observe the structure from this direction, then we can actually go with the Haworth projection formula. So what is that direction? So we know that this direction is actually the bond opposite to the bond between carbon number 5 and oxygen over here, right? So this is carbon number 5 and oxygen over here, and that bond which we need to, from where we need to visualize, that bond is opposite to it. So let me introduce you to the first of all these characters over here. You can see that this is that oxygen. This is the oxygen over here, right? This oxygen is represented by this red ball. All the black balls are representing the carbons. So 1, 2, 3, 4, 5 and 6th carbon over here. And all the white balls are representing the hydrogens, and the purple balls are representing the hydroxyl groups. Once again, I have not represented oxygen and hydrogen of the hydroxyl group with two different balls. I should have, but as you know, for the sake of simplicity, I have used just one purple ball over here. So now, Haworth is saying that if you want to visualize the structure drawn by me on this 2D surface in 3D, you need to look from this direction, which means like opposite the bond which is opposite to oxygen and carbon number 5. So this is oxygen and this is carbon number 5. The bond which is opposite to it is this one. So you need to visualize from this direction, like this. This is how you need to visualize this molecule. From here, you need to, here you are sitting the way I have arranged, right? So this is the how you need to visualize this molecule. You are sitting over here. So this represents this thing. Now let's see how the structure is. So this is the oxygen, which actually in the linear structure belonged to this carbon number 5 and attacked this carbon number 1, formed an ether bond with it. And after that, this carbon, which was actually the carbonyl group carbon, got converted into a chiral carbon and hemiacetyl carbon. This is the carbon number 1, and the position of H and OH on this carbon number 1 decides that which stereoisomer of this cyclic structure has been formed. Over here, the angle between the H and OH which is drawn is actually 180 degrees. So there is a straight angle between the two. But if you visualize over here, this carbon number 1, over here, you would just notice that there is no straight angle between the two groups which are bonded with this carbon, OH and H. This is again because the structure is tetrahedral with respect to this carbon. So there is a bond angle of 109 degrees once again. It is not 180 degrees, right? But for representation, again, very good, because it's like complicated to draw it and show it at an angle, right? But what about group which should be facing upwards and downwards? Here also you can notice that although it is at an angle, but one of the groups is facing upwards and another is going downwards, like with relative to each other. So if over here OH is up, so it means it is the beta form of this molecule. So this was about this carbon number 1, which is bonded with this oxygen over here, and we are visualizing from this side, right? The bond opposite to carbon number 5 and oxygen bond, this bond between carbon number 2 and carbon number 3. We are visualizing from this side. Then we come to the carbon number 2. On carbon number 2, again, it is bonded to carbon number 1 over here and carbon number 3 over here. Apart from that, 2 or more groups are H and OH. And now if you will look at this H and OH, the code for glucose is 245, right? So it means on the carbon number 2, the hydroxyl group is facing towards right. So any group which is facing towards right on the linear structure needs to face downwards in the cyclic structure. So over here on the group number 2, it is facing downwards. It is facing downwards, right? Then we come to carbon number 3. It would, as it is not mentioned in the code, so it means on the carbon number 3, hydroxyl group is on the right hand side of the carbon skeleton in the linear structure. So on the left hand side of the carbon skeleton, so it should be pointing upwards with respect to this hydrogen associated with this carbon over here on the carbon number 3. Then we come to carbon number 4. Then if you will see this carbon number 4 from this direction, again, so direction should remain the same, right? So if you will see this from this direction, then you will notice that even on this carbon, OH is pointing downwards and H is pointing upwards, but at an angle of 109 degrees, not at the angle of 180 degrees, no straight angle, just an obtuse angle over here, right? And again, because as the formula as the code suggests, is 245, means at carbon number 2 and 4 in the linear structure, OH is on the right hand side. That's why in the cyclic structure at carbon number 2 and 4, the hydroxyl group is pointing downwards. Then we come to the this carbon number 5 over here. On the carbon number 5, in the formula 245, it is mentioned that on the carbon number 5 also hydroxyl group is on the right hand side of the chain, but over here this carbon number 5 is no more left with the hydroxyl group. The oxygen is already bonded with the carbon number 1. So here actually it doesn't we are not dealing with this hydroxyl group orientation in the cyclic structures. We generally ignore the last position of the code. We just consider this 2 positions. Like for 245, if it is the code 245, we will just consider the position number 2 and position number 4, because we know that in the cyclic structure the 5th carbon is never left with its own hydroxyl group now. Right now, this 5th carbon over here is bonded with the hydrogen, and over here it is bonded with oxygen. So this carbon number 5 is bonded with oxygen, and then it is bonded with carbon number 6. This is the carbon number 6 bonding with the carbon number 6 with all of its groups. and then there is on the downside there is this hydrogen over here. So this is this carbon number 6 always points upwards for all the D form of stereoisomers. But if it would have been L-glucose, then this is represented over here downwards. So this is the Haworth projection formula for the D-glucose. But again, the rules remain the same, that we need to see the direction matters. If you are lost with the direction, you will lose whole of the structure. Nothing will make sense. So direction matters. Direction is what? That you need to visualize this from this direction. This direction. So we need to visualize this. So this is the Haworth projection formula. Now, I guess now you can easily see that how these 3D structures have been worked hard upon by the scientists to be represented in the 2D manner on the 2D surfaces, and how these 2D structures can be translated into the 3D forms, into the 3D forms, like it may be the Fisher projection formula, or it may be the Haworth projection formula. It can be anything, but we should be knowing the relationship between the two. Now, again, even this Haworth projection formula over here, it seems that all these groups are in the same plane, like this oxygen, this carbon number 1, this carbon number 2, this carbon number 3, 4, and 5. They all are in the one plane. Again, this is not true. Glucose, or for that matter, even the things which are in the form of furanose, even for the pyranose rings, it is not at all true, because sometimes this carbon number 1 goes down. So this is the oxygen and this is the carbon number 1, right? So if like right now it seems to be they are in the same plane, right? But sometimes it got tilted like this, it goes down like this, right? So if it has gone down like this, then this carbon number 4, which over here right now seems to be well bonded with carbon number 5 in the same plane, but this carbon number 4 gets tilted upwards like this. So this was the bond, it gets upped. Now this is tilted downwards and one is tilted upwards. Now these central 4 groups, they are in the same plane, no doubt, because this has been tilted downwards and it has gone upwards. When this happens, then this kind of chair conformation is formed. So this is the chair conformation. This chair conformation is formed. Carbon number 1 has gone down, and the carbon number 4 over here, this is carbon number 1, oxygen, carbon number 1, it has gone down, and this carbon number 4 has been tilted upwards with respect to the carbon number 5. Opposite can also happen, that this carbon number 4 may go down and this carbon number 1 may get tilted upwards. So in that case, headrest of the chair is over here is one formed by the carbon number 4, and the footrest is being formed by the carbon number 1. In that case, the headrest will be formed by the carbon number 1 and footrest will be formed by the carbon number 4. So this is one of the forms where the two carbons, carbon number 1 and carbon number 4, get twisted at an angle to the other 4 central groups, like these 4 groups, right? So if they are getting tilted opposite to each other, one going upward, another going downward, then always and always chair conformation is formed. But when they get twisted both upwards, like in the same direction, then this boat conformation is formed. This is the boat conformation which is formed. Now in this boat conformation, let's see, this is carbon number 1 and this is carbon number 4. This is carbon number 1 and this is over here, this is the carbon number 4, right? So if they get twisted, both of them get twisted towards each other, then this boat conformation is formed, right? All 4 in the same side, on the same plane, but these two carbons, this and this carbon, have just got tilted towards each other, then this boat conformation is formed. And this position over here is called bow and the stern positions. As when the two carbons just tilt upwards, then they come close to each other, and when they come close to each other, the groups bonded with them also come close to each other. Now, this coming too much closer is considered as invasion in each other's space, and they become uncomfortable with the situation, and then there is the situation of conflict over here, and which leads to instability of the boat conformation. So generally all the monosaccharides with the normal substituents, which means with the normal HOH substituents, don't form the boat conformations. If there is the boat conformation, then it is like in the traces. Generally, they form the chair conformation only. Both conformations are formed by the derivatives of the monosaccharides. Now, what are these derivatives of the monosaccharides? We need to discuss them. So before that, you can see these are the two kinds of chair conformations of glucose over here. The headrest is being formed by the carbon number 4, and footrest, the oxygen is bonded with carbon number 1, and footrest is formed by the carbon number 1 of the glucose molecule. And over here, the headrest of the chair is being formed by the carbon number 1, and footrest is formed by the carbon number 4. One more thing, all the groups which are going parallel to the axis of this structure, so there is the axis over here in the center, all the groups which are just parallel, this one is 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 parallel over here. So all these groups which are parallel to all these positions which are parallel to the axis of the structure, they are considered to be at the axial positions, and all those which are kind of perpendicular to the axis of the structure, they are considered to be the equatorial positions. Equatorial positions provide the stability because they are just kind of pointing away from the structure and having their own space. Then anything which is having its own space and comfortable in its space, any group, that leads to the stability. If they are like trying to interact with another, then more interaction, more conflicts, and more instability within the molecule. So we discussed that chair conformations are formed by most of the monosaccharides. Both conformations are formed by the derivatives of the monosaccharide, which we will discuss in the next video. Till then, goodbye and take good care of yourself.